Okay, so here's our first theorem about derivatives. So the theorem is the following. If f is differentiable at x0, then f is continuous at x0. So differentiability implies continuity. Okay? This is a certain, saying this statement is saying that a certain limit exists. The limit of f of x minus f of x0 divided by x minus x0 as x goes to x0. This is saying that a certain limit exists, just the limit of f of x as x approaches x0, and saying that it's equal to f of x0. Remember the definition of continuity? So I want to show that the existence of this limit implies the existence of this limit. Okay, so let's prove this. Proof. So we know, since we know it's differentiable, that the limit x goes to x0, f of x minus f of x0 divided by x minus x0 exists. Exists and is finite. That's the definition of being differentiable at the point x0, right? Okay. Now, let's look at this expression, f of x minus f of x0. I want to show that the limit of this thing as x goes to x0 is 0. If I show that this goes to 0 as x goes to x0, that means that f of x goes to f of x0. Right? Do you want me to write that? If we show that this goes to 0, this is a constant. This is some number. Call it L. If we show that f of x minus L goes to 0, that's the same as saying f of x goes to L. Okay, let's write this. Let's do it and write it. So I'm going to rewrite this, because I know this limit, I'm going to rewrite it as f of x minus f of x0 divided by x minus x0 times x minus x0. Do you agree that this and this is the same thing? I multiplied and divided by x minus x0. As x goes to x0, this goes to what? As x goes to x0, what's the limit of this expression? Not 0. Zero, wrong. Infinity, wrong. More answers? The derivative, good. This goes precisely to f prime of x0. That's the definition. The limit of this thing is f prime of x0, right? What about this thing? What does this go to as x goes to x0? This goes to 0, obviously. And therefore, the entire expression is a product of some finite number times 0, which is 0. So as x goes to x0, f of x minus f of x0 goes to 0, and therefore f of x goes to f of x0 as x goes to x0. And this is precisely the definition of continuity. The limit of f of x as x goes to x0 is f of x0. Questions?
Is there any specific reason why you choose to use either one of the limits?
Why do I choose the x and x0 or the h? In some cases, one is easier to work with than the other. In some cases, it really doesn't matter. And usually when one is easier to work with than the other, you just see it right away. I mean, this is what you want to show here. You want to show that f of x goes to f of x0. That's the definition of continuity. So it's kind of natural to take this rather than the one with the h. Okay? And I think that in all of the examples that we did of concrete functions, it just makes no difference. Both would work equally well. Okay? So here's our Helmholtz, and this completes the proof. So differentiability implies continuity. Remarks. So remark 1, the converse is false. Being continuous does not guarantee being differentiable. Can somebody give me a counterexample? Good. It's on the board. I didn't erase it. Here it is. Absolute value of x is continuous, right? But it's not differentiable at 0. Okay? So the converse is false. Counterexample. Absolute value of x. Continuous at 0. Continuous at x equals 0, but not differentiable at x equals 0. Okay, so that's the first remark. The second remark, so this is not going to be the converse, it's going to be re-saying the same statement, but in the counter direction. So if f is not continuous, then f is not differentiable. Because if it were differentiable, it would have to be continuous. So one way of saying automatically that a function is not differentiable is, well, it's not even continuous, so of course it's not differentiable. Okay. And I want to quickly define one-sided derivatives. So I'll just write the formulas and not tons of words. So f prime, this is the notation, f prime plus at x0 is defined to be the limit defining the derivative, but when you approach only from the right. So the limit as x goes to x0 plus of f of x minus f of x0 divided by x minus x0. So this is the one-sided derivative at the point x0 if the limit exists. Okay? And f prime minus at x0 is the same thing as x approaches from the left. And you can, of course, define it similarly with the h's, and you just have to show to say if the limits exist. If they don't exist, then it's not differentiable, and f prime is not defined. Okay, so these are the one-sided derivatives. Good? Okay. So as we said before the break, we don't want to resort to the definition of the derivative, namely taking that limit every time we want to calculate a derivative. We want to have some more powerful tools, and those, of course, exist, and I assume that, in fact, you probably know at least many of them. So here's the very basic ones. So this is the arithmetics for derivatives, but it's very different than regular arithmetics. I'll write it and you'll probably recall. So rules for differentiating. So the assumptions are going to be let f and g be differentiable at x0. Then 1. So first of all, when you multiply by a constant, so you take c times the function f, and take its derivative at x0, that's the same as taking the derivative of f itself at x0 and multiplying it by c. So the constant, you can just take it out of the derivative. Okay? This is for any c in R, constant. 2, if you take the sum of two functions, f plus g, and take its derivative. Let me not write the x0 all the time, because it's easier to remember when you don't have to say out loud the x0. So f plus g prime equals what? Right, f prime plus g prime. And likewise, you can write it for minus. And this follows, if you want to prove number 2, for example, or number 1, it follows immediately from the definition of the derivative using the limit. You can easily prove these on your own. These are completely straightforward. Okay? The plot thickens when you look at the product. So wouldn't life be nice if fg prime would be f prime times g prime? But you know that's not true. Right? So what is it? Do you remember what is true? Right. F prime g plus g prime f. Okay? You all know this, right? The product rule. Right? And finally, the quotient rule, which is even more intimidating. F divided by g prime is what? F prime g minus g prime f, and then there's dividing by g squared here, and this is, of course, g has to not equal 0 at the point x0, but I'm not writing the x0 all along because it just confuses. Okay, you all know these, right? The quotient rule and the product rule. Okay, I want to prove one. I want to show you how come this suddenly happens? How does it happen? Okay, so let me prove it. The proof is not long, and you see right away what's going on. So I want to prove number 3. Proof of the product rule. Proof of the product rule. So what do I want to prove? I want to find the derivative of f times g. The only thing I can resort to is the definition of the derivative. Okay? So I want the derivative of f times g, so I have to choose one of these. Instead of writing f, I'm going to write fg and calculate the limit. Okay? So I'm going to choose this one here. So I want to calculate the limit, and I'll do the limit as arrow at the end. So I want f times g at that point, so f at x0 plus h times g at x0 plus h minus f at x0 times g at x0. All of this divided by h. That's plugging in fg here. Do you agree? And I want the limit of this as h goes to 0. That would be the derivative of fg. Does everybody agree?
Why is it not h squared on the bottom?
No, I'm just plugging in fg here. That's the derivative of fg. Everything else remains the same. Good? Okay. So I'm going to do a standard, completely standard thing here. So this long line in the h on the bottom, I'm just going to write as 1 over h here. And I'm going to, in order to get expressions that I know something about, I'm going to add and subtract a certain term. So I'm going to get f, it's going to be a long line, f at x0 plus h times g at x0 plus h. That's this thing. I just copied it. Then I'm going to subtract f at x0 times g at x0 plus h. This is a new term. I subtracted it. I'm right away going to add it back. And then I'm going to subtract this original thing. So I added and subtracted the same thing, therefore this equals. Do you agree? Good? Okay. And now I'm going to break it into two terms that I actually know something about. So the first one is going to be this. I'm going to write it. Do you see that g of x0 plus h appears in both? So I'm going to take it out, g of x0 plus h. And what I have left is f at x0 plus h minus f at x0. And then I'm going to throw in this dividing by h here. So that comes from these two terms. Do you agree? Now, on these two terms, f at x0 is the common factor. So I'm going to write plus f at x0. And then what I'm going to have left is g at x0 plus h minus g at x0. And then there's that 1 over h that lived out here. I'm going to throw it back in. Does everybody agree to the algebra? And do you see where I'm heading? Good? Okay. Now let's remember what I want to do. I want the limit of this thing, as h goes to 0. That's what I'm interested in, right? That's the derivative, by definition. So what does this expression here go to as x goes to 0? As h goes to 0, what's the limit of this expression? Right. This is precisely g prime at x0. By definition. This is the definition of the derivative for g. So this goes to... Ooh, I'm out of space here. So I'll do it diagonally. This goes to g prime at x0 as h goes to 0. Does everybody agree to this? What about this thing? What about this? What about this? F at x0. This is a number. As h goes to 0, this constant just remains the constant. So this goes to f at x0. Do you agree? It's fixed. It doesn't depend on h at all. What about this term here? This goes to f prime at x0. Do you agree? And finally, what about this thing? As h goes to 0, g of x0. Now the only thing that's that still requires a slight justification is this one. What's the justification needed here? Very good, very good. As h goes to 0, clearly x0 plus h goes to x0. But why does g respect that? Why does g of something go to g of the limit of the something? Because g is continuous. Only a continuous function would satisfy this. Do you agree? Think of x0 for a minute as just being 0. Okay? So the statement here is that g of h goes to g of 0 as h goes to 0. That's precisely saying that g is continuous. It doesn't hold when g is not continuous. Do you see that? So this statement holds, this specific limit is true since G is continuous. And why is G continuous? That's not an assumption of the theorem. The assumption is that these two functions are differentiable. Right. It's the previous theorem. If the function is differentiable, that implies that it's continuous. So all in all, what did we get here? We got here precisely gf prime plus fg prime, which is not the order we spelled it there, but it's the same thing. So we get f prime g plus g prime f, of course, at the point at x0. You have to put in the x0s all along, and I'm out of space here. Questions? Yes?
Could you say that g of x 0 plus h goes to g of x 0? Right?
This is true only because we know that g is continuous. Otherwise, this would not necessarily be true.
So why over there?
Here?
No.
Here?
Yeah, why up on the numerator?
Here?
Yeah, g of x, why don't we say that that is also g of x 0 and then...
No, the limit of this difference, since g is continuous, this goes to g of x0, so just the numerator goes to 0.
Yeah.
But the denominator goes to 0 too. So this is a 0 over 0 situation, and in general you have to calculate it, but here you don't have to calculate anything because you know it exists, and this is what it is, by definition. Okay, that's precisely this. This is saying that g is differentiable at x0. Okay? Yes?
Wouldn't we be able to, instead of using x0 as, let's say, like, the point that we're dealing with, could we just say generally it's a function of x?
You want to, instead of writing x0, write x?
Yeah.
You can do that. You can do that. It's the reason I add this 0 is to somehow emphasize that throughout this entire calculation, x0 is fixed. It's not a variable.
No,
Okay?
Why do you want to emphasize that? Like, what?
Because that's the whole definition. The whole definition is a pointwise definition. Saying that a function is differentiable at x0 is fix x0. This limit exists for x0. Here x is a variable, right? So, and here h is the variable. That's why I took the limit as h goes to 0. So if you write here x, it might confuse you that x, x is thought of as a variable. Okay, and x0 is somehow pinning it down and saying, now it's fixed. It's a specific x. And that's this statement. Okay, so that's the product rule. I'm not going to prove the quotient rule, which is written here, but you can see why these limits, look here a second, this is the quotient rule. You can see why these limits are not going to just be the naive f prime over g prime. You can see why there's no reason for that to happen. If you just do the first line of the proof, plug in the expressions you want to take a limit for, there's no reason for it to be the quotient of the derivatives. Okay, and if you run through the calculation, you'll see that this is what happens. Okay? Okay. So that's rules for differentiation, but there are more. So what's the next one that I want to write? We took care of sums and differences and multiplying by scalars and products and quotients. What's the next thing we can do with functions? Right, we can compose functions. Right? So let's write that. Theorem. So if f is differentiable at x0, and now I want to compose it with g. Okay? So I'm not going to assume that g is differentiable at x0. Where do I want g to be differentiable? At f of x0, right? And G, that was a weird G, and G is differentiable at f of x0, then, and now I have the formula for the derivative of a composition. Do you know the name of this theorem? It has a name? Right. This is called the chain rule. Chain rule. But what it is really the formula for the derivative of a composition. So I have G composed with F. I want to take the derivative of this at the point x0. And what do I get? You know this, right? What do I get? I get the derivative of G itself, where it's defined, at f of x0, times f prime at x0. Do you know what this is called? This has a name. It's called the inner derivative. Have you heard that? Inner derivative. So I'm taking the derivative of G at f of x0 and multiplying it by the derivative of f at x0. That's this theorem. Okay? Let's do some examples. Okay, let's write the first example here. Suppose I want to find the derivative of cosine of x. The derivative of cosine of x. One way to do it is to resort to the definition of the derivative. Just like we did for sine, do it for cosine. There's going to be a certain trig identity for the cosine of alpha minus cosine of beta. You can do it. It's going to be very, very similar. I want to do it a bit differently. So do you agree that cosine of x is the same as sine of x plus pi over 2? And then I wanted to take the derivative of that. Cosine is the same as sine of x plus pi over 2. Another way of saying it is that the graph of cosine is a shift of the graph of sine by pi over 2. Take the graph of sine, shift it, you get the graph of cosine. Do you agree? Does everybody agree to this statement? So now I want to take the derivative of this thing. And what is this thing? This is a composition. It's sine, that's the g here, that's the outer function. And the inner function is just x plus pi over 2. So now I'm going to use the chain rule to take the derivative. And what does the chain rule tell me? The chain rule tells me, take the derivative of sine itself, right? What's the derivative of sine? Cosine. That we already know. We proved it. So it's cosine evaluated where? Not at x. At f of x. At x plus pi over 2. Right? And multiply it by the inner derivative. The derivative of this thing. What's the derivative of this thing? 1. Because it's the derivative of x, which we calculated, 1, plus, because of addition of derivatives, the derivative of pi over 2, which is 0, because it's a constant. We calculated that as well. So do you agree to this? So that's it. That's the derivative of cosine of x. That's not what you're used to seeing. And what you are used to seeing is, well, what's cosine of x plus pi over 2? It's again a shift of sine, but you want to shift, you want to add pi over 2, so you're shifting to the left. So in fact, this is minus sine of x. Okay? If you're having trouble seeing this, draw them. Draw sine x, draw cosine x, draw sine of x plus pi over 2, and see that this and this are precisely the same, and then this and this are precisely the same. You'll see it right away if you draw them. Okay? But by staring at them, if you're confused, that's not going to help your confusion. Draw them. Okay? So the derivative of cosine is minus sine. Yes?
What do you get from the step of sine of x plus pi to 2?
From here to here?
Yeah.
Chain rule. Chain rule. Precisely this theorem up here. This is a composition of two functions. The outer function, the g, is sine. The inner function, the f, is x plus pi over 2. By this rule, you have to take the derivative of g, which is just cosine, evaluated not at x, but at f of x, multiply it by the derivative of the inner function, 1. Good? Here's another example. So I stopped enumerating our examples today. What example was this? This was, we had like 5 positive ones, and then we had the other. This would be 7, right? Example 7. And let's call the next one example 8. Example 8, suppose I want to take the derivative of tangents of x. Note that I'm not writing the x0 all the time. Okay, so since it's true for any x0, I'm just not writing it, just like we didn't write it in the rules themselves. Okay, so again, I can try doing this by definition, or I can manipulate it and use the theorems that I already know. Right. Tangents of x, it really calls for writing it as a quotient and taking the derivative of the quotient. And now we know how to take derivatives of quotients, because that was rule number 4. And we know the derivative of sine. We calculated it using the definition. And we know the derivative of cosine, because that was example 7. So now we have all the ingredients we need to cook the answer here. So now I'm going to use the quotient rule for derivatives. So this is f, this is g. It's f prime g minus g prime f divided by g squared. That you just have to remember. Okay, if you don't remember that, just say it to yourself 15 times until you remember it. You just have to remember it. So, what's the derivative of sine? Cosine. This is f prime times g, cosine squared, minus the derivative of cosine, negative sine, so it makes this into a plus, times f without the derivative. So again, we get sine squared, divided by the bottom squared, g squared. Do you agree? What is the top? It's just 1. So we get 1 over cosine squared of x. You can remember it like this, or, right, you can remember it as secant squared. 1 over cosine is called secant. Doesn't matter. I prefer not to even know those functions. Whenever you need to use them, you can use these with just the same.
Are we going to work with secants and cosecants?
You can work with secants and cosecants, or you can work with 1 over cosines and 1 over sines. It's the same thing, so why add those two?
Just for limitation, think it was close.
I'm not going to use them. Okay, but you should know what they are, and in particular, it's probably not a bad idea to know what their graphs look like. But okay. So this is the chain rule and the product rule and so on. Now I'm going to write the last rule, the last standard rule for differentiation which we have. Where am I going to write it? I'll write it here. And that's the rule for taking derivatives of inverse functions. Okay? It's going to look a bit scarier in terms of the statement of the theorem, but using it is not hard. So, theorem. So this is the rule for differentiating an inverse function. So let y equals f of x be invertible and continuous. You need to request continuities. Well, yeah. You need, okay, some things you're not going to see why we need them. They're required for the proof, and we're not going to prove it. So this continuous at a neighborhood of x0, and you're not going to see why we need this. So invertible, continuous at a neighborhood of x0, and differentiable at x0. That's obviously something you need. Also, assume that f prime at x0 is not 0. And that we need since we're going to divide by it. Then, f inverse of y, or x equals f inverse of y, this is the inverse function. Remember what an inverse function is? It's a function going from the y's to the x's, and if you put an x here and get a y, this function to that y has to reproduce the original x. Remember what the inverse function is? Okay, so f inverse is differentiable at y0, which is f of x0. And there's a rule for finding the derivative. So f inverse prime, don't be confused by this minus 1 and this prime, f inverse prime at y0 is precisely 1 over the original f prime at x0. Okay? So don't get blurred by all this data. This is the formula. Okay? You take an inverse function, you want to find its derivative. That's 1 over the derivative of the original function at the corresponding point. Okay? So f at x0 has to be y0. That's the statement. Okay, let's do an example. Do we have time for an example? Yes, we do. Good. So let's do an example. Example. Okay, there are several of them here. Okay. Suppose you want e to the x. You want the derivative of e to the x. Okay. But I'm not going to call it e to the x. I'm going to call it, so let me write it like this. We know that the derivative of ln of x is 1 over x. This is for x is greater than 0. Right? This was the example that I left the details for you to work out. Right? So we know this. The inverse function, so this is example number 9. The inverse function of y equals ln of x is what? What's the inverse function of ln of x? E to the x, but I wanna stick to the variables. This is important when you use this. So it's x equals e to the y. Do you agree? Right? That's the inverse function. So what's the derivative? Hence, e to the y prime is what? 1 over ln of x prime. That's what that formula tells us. Do you agree? E to the y prime is 1 over the original function prime. So what is ln of x prime? So it's 1 over x, which is x, right? But remember what x was? E to the y. So the derivative of e to the something is e to the something. I'm guessing you knew that as well, right? Good? Okay. Hmm? Yeah, I just proved that I proved it using the theorem, which I didn't prove, for the derivative of an inverse function. But once you prove that theorem, this is the proof that the derivative of e to the something is e to the something. Okay, that this function is not affected by scissors. Okay? Okay, one more example. Example 10. Example 10. Arc sine of y prime. So what is it? It's 1 over, arc sine is the inverse function of sine, of 1 over sine x prime. Do you agree? So here I use the theorem, the derivative of the inverse function. What's sine of x prime? 1 over cosine of x, right? But now I want to go back to the y's. I can't leave it like that. And the problem is, if I had sine x here, that would be easy, right? That would be just 1 over y. But it's not sine x, it's cosine of x. So I have to do an extra manipulation step. So cosine squared is 1 minus sine squared. So cosine is the root of 1 minus sine squared. Do you agree to this? Right? This is just using the formula cosine squared plus sine squared equals 1. And now, sine of x is y. That's, if arc sine of y is x, then sine of x is y. So this is precisely, so sine x equals y. That's the inverseness I'm using here. 1 over the root of 1 minus y squared. This is the derivative of arc sine. Good? Okay, so try on your own, try arc tan. Try to find the derivative of arc tangents of y. Okay, do you know what the answer is going to be? This has a key role in integrals, this thing. Right, the answer, so answer 1 over 1 plus y squared. That's the derivative of arctan. Okay, so let's stop here for today. Next time, the theorems from the very, very first lecture, Fermat, Rolle, and Lagrange, with a full discussion, and now we're going to see how those intuitive drawings that we had, that we did in 20 minutes in the first lecture, how they translate to formal definitions now that we can define continuity and differentiability, and now that we've built up the theory, we can actually handle those theorems formally. Okay.